Welcome to our quantum deep dive.
Hello.
Get ready to plunge deep into the building blocks of reality today because we're focusing on one of the most fascinating particles out there, the bottom quark.
It really is fascinating, often just called the b-quark, but, it's far from basic.
Yeah.
As we'll explore, it holds keys to some pretty big mysteries in the universe.
Yeah, and maybe even hints about future technologies like quantum computing.
Exactly that. It's surprisingly connected.
Our guide for this journey is an insightful essay, Bottom Quarks, Fundamental Baustein der Quantentechnologie by Jörg O. Schneepapp.
A great starting point.
So our mission in this deep dive is to really understand the bottom quark, what it is, why it's so absolutely essential in particle physics, and our understanding of the cosmos.
And crucially, how its peculiar nature connects, maybe unexpectedly, to the world of emerging quantum technology.
So prepare for a bit of a wild ride into the subatomic. We'll be touching on questions like, well, why matter exists at all?
A pretty big one.
Definitely. And the hunt for brand new forces, and yes, even the physics behind tomorrow's potentially unhackable encryption and powerful computers.
Lots to cover.
Okay, let's unpack this then. When we talk about bottom quarks, what exactly are we dealing with?
Think of them as one of the fundamental Lego bricks, sort of, that the universe uses to build everything. They are one of 6 types or flavors of quarks.
Flavors, right.
And these quarks are considered elementary particles, meaning, well, as far as we know, they aren't made of anything smaller. The B just stands for bottom.
6 flavors. Okay, so where do they fit in the bigger picture, like the standard model of particle physics?
Right. The standard model kind of organizes all these fundamental particles. Quarks come in 3 pairs, or generations.
Okay.
You've got the familiar up and down quarks in the first generation. They combine to make protons and neutrons, the core of every atom around you.
The everyday stuff.
Pretty much. Then there's the second generation, charm and strange quarks. They show up in more exotic, less stable particles, usually created in high-energy collisions.
And the bottom quark is in the 3rd generation, then?
Exactly. The 3rd generation contains the heaviest quarks, the top and the bottom, and the bottom quark is the second heaviest of all the quarks.
Only beaten by the top quark.
Right, which is truly colossal in mass terms.
Heavy, got it. What are some of the other need-to-know properties?
Well, they're fermions. That means they have a specific kind of intrinsic angular momentum called spin 12, basically.
Okay.
Which dictates how they behave quantum mechanically, Pauli exclusion principle and all that.
Yeah.
They also carry an electric charge, specifically negative 1/3 the charge of an electron, minus 130.
Minus 1/3.
And as you mentioned, their mass is substantial for a particle, about 4.18 GeV.
Which sounds like a number, but how does that compare?
Well, to give you a sense of scale, a proton's mass is less than 1 GeV. So the bottom quark is actually heavier than a whole proton.
Wow, heavier than a proton.
Yeah, but still much, much lighter than the top quark, which is heavier than an entire gold atom. It's a huge range.
That's incredible. But they don't stick around long, do they? You said they were unstable.
No, they are fleeting indeed. Their high mass means they decay very quickly via the weak nuclear force, another one of the universe's fundamental forces.
How quickly?
Their average lifetime is incredibly short, something like a trillionth of a second. Yeah. About 1.3 by 10 little seconds.
Gone in a flash.
Pretty much. They also possess something called color charge. Red, green, or blue. Not literal color, of course.
Right, it's a quantum property.
Exactly. Related to the strong nuclear force, which is carried by particles called gluons.
Okay, color charge and strong force. This connects to something really fundamental about quarks, doesn't it? Like, we never actually see one on its own.
That's right, and it's one of the most sort of counterintuitive things about them. They are subject to quark confinement. Yeah, the strong force that binds them together has this peculiar property. It doesn't get weaker with distance, like gravity or electromagnetism. It actually gets stronger.
Stronger? That's weird.
It is. It's like trying to stretch an incredibly strong quantum rubber band. The further you pull the quarks apart, the harder the force pulls them back. Eventually, it's easier to create a new quark-antiquark pair from the energy than to separate them.
So they're always bundled up then, never free.
Precisely. They're always found inside composite particles called hadrons.
Hadrons, okay, like protons and neutrons.
Yes, those are baryons made of 3 quarks, but there are also mesons, which are made of a quark and an antiquark.
Yeah.
And the famous b-mesons, which we'll talk a lot about, are typically made of a bottom quark and a lighter antiquark.
B-mesons, got it.
Mm-hmm.
And how did we first figure out these heavy, confined particles even existed? Must have been tricky.
It was a landmark discovery back in 1977 at Fermilab. Researchers observed a new particle. They called it the upsilon meson. And they realized it had to be a bound state of a bottom quark and its antiparticle, an anti-bottom quark.
So finding the upsilon was the proof.
It was the crucial evidence, yes. It confirmed the Standard Model's prediction that there should be a third generation of quarks.
So, discovered relatively recently, heavier than a proton, always stuck inside other particles. Why are bottom quarks so incredibly important for particle physics and, understanding the universe?
Well, their significance really comes down to their unique properties and how they interact. They feel the strong force interacting with gluons that's described by quantum chromodynamics, or QCD.
Right.
And crucially, they also interact via the weak force, which is what governs their decay. And that decay is where things get really, really interesting.
Especially with this concept you mentioned earlier, CP violation.
This is arguably their most celebrated role, yes. CP symmetry is a fundamental concept in physics. It combines C, charge conjugation, swapping a particle for its antiparticle, and P, parity, which is like flipping spatial coordinates looking in a mirror.
Okay, particle swap plus mirror image.
Exactly. And the laws of physics should look the same if you applied this combined CP transformation. That was the assumption for a long time.
But the universe doesn't quite play by that rule.
Not completely, no. We observe what's called CP violation in certain particle decays. It means the laws of physics are actually slightly different for a particle compared to its CP-flipped antiparticle equivalent.
A slight difference.
It's a subtle asymmetry, yes, but it has absolutely profound consequences.
And B-mesons, the ones with bottom quarks, they're perfect for studying this asymmetry.
They turned out to be ideal testbeds, yeah. Their decay patterns show this CP asymmetry in ways that are, well, relatively easy to measure compared to other systems.
Easier to measure, okay.
So, pioneering experiments like BABAR at SLAC in the U.S. and Bell at KK in Japan were specifically built to study B-mesons in enormous numbers. They produced billions of them.
Wow.
And their precise measurements of CP violation in these B-meson decays were a huge confirmation of the theory and actually led to a Nobel Prize in Physics in 2008 for Kobayashi and Miskawa, who predicted it.
So, studying these tiny B-mesons, how they decay slightly differently, this is somehow connected to the biggest question of all, why the universe exists as it does, why it's made of matter.
Absolutely. This asymmetry, this CP violation, is one of the essential ingredients, one of the Sakharov conditions needed to explain why the universe today is dominated by matter.
Instead of
having equal amounts of matter and antimatter, which would have formed in the Big Bang, then just annihilated each other completely, leaving nothing behind but energy. No stars, no galaxies, no us.
Right, annihilation.
So the CP violation seen with b-quarks, which is predicted by the Standard Model through something called the CKM matrix, contributes to this explanation. It allows for slightly different decay rates for matter and antimatter.
But is it enough? Is the Standard Model's CP violation sufficient?
That's the million-dollar question. Or maybe billion-dollar, given the experiments.
Probably.
The amount of CP violation we actually see coming just from the Standard Model via these quark interactions doesn't seem to be large enough on its own to explain the full matter-antimatter imbalance we observe in the cosmos today. There's a big gap.
Which strongly suggests what?
That there must be other sources of CP violation out there. Sources that come from new physics, physics beyond the Standard Model.
I see.
And so studying bottom quark decays with ever-increasing precision is one of our best hopes for finding clues about this new physics, for finding these missing pieces of the puzzle.
And besides CP violation, they also help us test the strong force itself, QCD.
Yes, definitely. Because they're heavy and interact strongly, bottom quarks provide unique ways to probe quantum chromodynamics. Studying how they behave when bound inside hadrons allows us to test the predictions of the strong force theory.
Especially the tricky parts.
Exactly, including aspects that are very difficult to calculate or model theoretically without experimental input. Heavy quarks are a great laboratory for QCD.
Okay, so they're fundamental within the Standard Model, critical for this cosmic asymmetry question, and a probe for QCD. This brings us neatly to how bottom quarks act as a sort of window to physics beyond the Standard Model.
Right, because the Standard Model, while incredibly successful, we know it's incomplete. It doesn't explain dark matter, for instance.
Or dark energy.
Or dark energy, or the masses of neutrinos, or fully account for that matter dominance we just discussed. There are big holes.
And b-quark experiments are actively looking for signs of things that could fill those holes.
Precisely. Experiments like LHCb at CERN, the Large Hadron Collider Beauty Experiment, and the upgraded Belle-Tunce experiment in Japan are pushing the boundaries of precision measurement.
How do they do that?
They measure the properties of bottom quark decays, like exactly how often certain decays happen, what specific particles they decay into, the angles and energies involved, all with incredible accuracy. And they're looking for tiny deviations, tiny discrepancies from what the standard model predicts.
And any deviation would be huge news.
No, absolutely. Even a slight difference could be the fingerprint, the first tangible evidence of new, undiscovered particles or forces influencing the decay process behind the scenes.
What kinds of new physics are they specifically looking for using bottom quarks? Any examples?
Well, they're searching for signs of many hypothetical theories. For instance, theories like supersymmetry or cis-UFY.
Ah, yes. What?
Which proposes a whole zoo of new, heavier partner particles for every known particle. These hypothetical supersymmetric particles, if they exist, could subtly alter the way bottom quarks decay, maybe changing decay rates or angular distributions.
Okay, so looking for indirect effects.
Exactly. And they also investigating some really fascinating anomalies that have actually popped up in some measurements over the last few years. Hints, perhaps.
Anomalies? Like what?
Well, one prominent area is potential violations of something called lepton flavor universality.
Lepton universality. Sounds important.
It is in the standard model. It basically predicts that certain interactions should be exactly the same, regardless of whether an electron, a muon, or a tau lepton is involved. They're all leptons, just different flavors.
They should be treated equally by the forces.
By the weak force in certain decays, yes. But some measurements, particularly at LHCb, looking at specific B-meson decays, seem to suggest small differences in the rates, depending on whether electrons or muons are produced.
Really?
Yeah, the results are still debated, need more data. But if these hints solidify and are confirmed, that would be a clear, undeniable sign of new physics, something beyond the standard model interacting differently with different leptons.
Wow. And even potentially connections to dark matter.
Indeed. While dark matter itself doesn't seem to interact strongly or weakly in obvious ways, that's why it's dark, some models propose dark matter candidates that could perhaps be produced in extremely rare bottom quark decays.
So looking for missing energy or weird signatures.
Exactly. Experiments search very carefully for these incredibly faint signals, these very rare processes that aren't predicted by the standard model, which might involve dark sector particles.
Okay, this is where, as you said, it gets really interesting. How do these incredibly small, fleeting particles, born from high-energy collisions, connect to something as practical sounding as the cutting edge of quantum technology? It seems like a massive leap.
It does seem like a leap, doesn't it? And from fundamental particles to future tech. But the essay highlights some fascinating conceptual links and also some practical spillovers.
Okay.
I mean, obviously, you're not going to build a quantum computer out of bottom quarks directly. They decay way too fast.
Right, that wouldn't work.
But the physics they embody, the quantum rules they follow, and importantly, the methods and technologies we've developed to study them, these are highly relevant to quantum tech.
Okay, tell me more about the connection to quantum computing then.
Well, think about the quantum world itself. It's all about probabilities. Superposition being in multiple states at once, and entanglement, that spooky connection between particles.
The core quantum concepts.
Exactly. And the decay of a bottom quark is fundamentally a quantum process. It's governed entirely by quantum probabilities. Studying how these quantum states evolve and decay in B-mesons offers a natural, albeit a complex system, for understanding these core quantum principles in action.
And could we use quantum computers to understand them better?
Absolutely. That's a huge potential application. Simulating the complex behavior of quarks bound together by the strong force, the realm of QCD, is computationally extremely challenging, even for the world's biggest classical supercomputers.
Too many interactions.
Way too many quantum interactions to track accurately. But this is precisely the kind of complex quantum simulation problem that future, fault-tolerant quantum computers are expected to excel at. They could allow us to gain much deeper insights into quark confinement, hadron structure, maybe even CP violation itself.
Interesting. What about quantum cryptography making unbreakable codes? How could d-quarks possibly help there?
One key element in modern cryptography is true randomness. Generating genuinely unpredictable random numbers is vital for secure keys.
Right. Pseudorandom isn't perfectly secure.
Exactly. But quantum mechanics provides sources of true inherent randomness. The precise moment a specific bottom quark decays is fundamentally unpredictable. It's governed purely by quantum probabilities.
Ah, I see.
So this spontaneous quantum randomness observed in particle decays can, in principle, be harnessed to build true quantum random number generators, or QRNGs.
Using particle decays as the dice roll?
Sort of, yeah. These QRNGs are crucial for generating cryptographic keys that are genuinely random and thus theoretically unhackable by any computer, classical or quantum, that tries to predict them.
And could the properties of b-mesons themselves be used cryptographically, not just the randomness?
Potentially, yes. This is maybe more speculative, but properties like the very precise oscillation rates of neutral b-mesons.
Oscillations.
Yeah, b-mesons can actually spontaneously flip back and forth between being a matter particle and an antimatter particle before they decay. It's a purely quantum mechanical effect called mixing.
That's bizarre.
It is, and it happens incredibly rapidly and predictably on average. Some researchers think these kinds of precise quantum phenomena, perhaps related to b-meson oscillations or decays, could conceivably be used to build novel physical systems for generating cryptographic keys or proving identity, things that would form the basis of what's called post-quantum cryptography.
Methods resistant to attacks by future quantum computers.
Exactly, using physics itself to secure information.
Okay, what about precision measurement and sensing? You mentioned oscillations.
Right, those b-meson oscillations, flipping between matter and antimatter, happen extremely rapidly and with remarkable predictability, governed by fundamental parameters. This makes them behave a bit like incredibly precise quantum clocks.
Like atomic clocks, but subatomic?
Kinda, yeah. In principle, this type of phenomenon could serve as a basis for next-generation timing devices, or potentially highly sensitive tools for measuring fundamental constants of nature with even greater accuracy.
And the technology built to actually find these b-mesons, does that help?
Oh, hugely. That's another really practical connection. The detectors used in experiments like LHCb and Beltasec are some of the most sophisticated and sensitive instruments ever built by humans.
They have to be, right, to catch these tiny decay products.
Absolutely. They're designed to track the fleeting decay products of particles like b-mesons, reconstructing their paths and measuring their properties with incredible speed and spatial precision, often in environments flooded with other particles.
So the tech itself is cutting edge.
Extremely.
Yeah.
The technologies developed for these particle physics detectors, things like novel silicon pixel sensors, very high-speed data transmission and processing electronics, sophisticated algorithms for pattern recognition.
Right.
These are directly applicable or can be adapted for developing advanced quantum sensors for other purposes, maybe quantum imaging devices, tools for quantum metrology, the science of ultra-precise quantum measurement.
Like measuring other faint signals.
Potentially, yes. Yeah. Maybe adapting detector tech to look for elusive particles like neutrinos, or perhaps even searching for subtle gravitational wave signals using atom interferometry techniques inspired by particle detection.
It's amazing how the hunt for the absolute smallest things drives the development of these incredibly sensitive tools that might then be used for completely different purposes.
It's a classic case of fundamental science driving technological innovation, isn't it? And one more thing, the entanglement that occurs naturally during particle interactions, including those involving bottom quarks.
That's spooky action at a distance.
Yeah. Understanding and controlling entanglement is key for quantum communication. Studying it in particle systems, even conceptually, informs the development of future quantum networks.
So this whole journey has really shown how the bottom quark sort of bridges fundamental physics and future tech. But as with any cutting-edge field, there must be big theoretical challenges and open questions remaining, right?
Yeah, absolutely. Plenty of them. One of the most perplexing mysteries, really, is the quark mass hierarchy problem.
The what now?
The quark mass hierarchy, basically. Why are the masses of the 6 different quark flavors so dramatically different? They span like 5 or 6 orders of magnitude.
You mentioned the up is tiny, the bottom is heavier than a proton, the top is heavier than gold. Exactly.
Why these specific values? From the tiny up quark mass, just a couple of MeV SOCs up through Charm and Strange, then the bottom quark significant 4.18 GeV psi, all the way up to the incredibly heavy top quark at around 173 GeV psi. Why this enormous spread? Why this particular pattern?
And the standard model.
Yeah.
It links mass to interaction with the Higgs field, doesn't it?
It does, yes. Mass arises from how strongly each particle couples to the Higgs field that permeates spacetime. But the standard model doesn't explain why the strength of that coupling, the interaction strength, is so vastly different for each individual quark flavor. It just puts the measured values in as parameters. The mass values seem almost arbitrary within the model itself. There's no explanation for the hierarchy.
So could this hierarchy be a signpost, pointing towards new physics?
Many physicists strongly suspect it is, yes. It feels like a clue. It suggests there might be some deeper structure, maybe a new symmetry or mechanism we don't yet understand, that dictates these fundamental mass parameters and explains the pattern.
Okay, and carrying that thought even further, are quarks truly fundamental? Or could they maybe be made of even smaller particles? Is that still a thing?
Well, the essay does briefly touch on this hypothetical idea. There have been speculative theories over the years proposing preons, even more fundamental constituents that might make up quarks and leptons.
Like layers of an onion.
Sort of. However, it's really crucial to emphasize. There is currently zero experimental evidence whatsoever supporting the existence of preons or any quark substructure. All experiments so far are consistent with quarks being point-like fundamental particles. It's an idea that's out there, but not driven by data right now.
Got it. Pure speculation for now. And just circling back finally to that matter dominance mystery.
Yes, the CP violation link. While CP violation in bottom quark decays, mediated by the standard model CKM mechanism, is absolutely a vital piece of the puzzle.
We know it's not enough.
Right. The big open question remains,
Yeah.
is the amount of CP violation observed within the standard model sufficient? Almost certainly not. So is the study of b-quark CP violation actually guiding us towards needing additional and perhaps much stronger sources of CP violation?
Sources originating from that physics beyond the standard model.
Exactly. New particles, new interactions that violate CP symmetry more strongly, needed to fully explain why matter overwhelmingly won out over antimatter in the cauldron of the very early universe. B-physics is a key tool in that search.
So, looking back at our deep dive today, we've really seen how bottom quarks, these minuscule, incredibly short-lived particles, are actually central to our understanding of fundamental forces.
Both strong and weak.
Central to our search for physics beyond the standard model, essential for tackling cosmic mysteries like the matter-antimatter asymmetry.
A huge question.
And even, surprisingly, inspiring concepts and technologies for the future of quantum computing, cryptography, and sensing. It's quite a portfolio for one little particle.
It really is, and it beautifully illustrates this incredible interplay we see so often in science, doesn't it? The quest to understand the absolute smallest components of reality.
Drives innovation in cutting-edge technology, creating new tools.
And then, in turn, future technology, like perhaps quantum computers, promises to give us powerful new tools to simulate and understand those fundamental components better than ever before. It's a virtuous cycle.
It definitely leaves us with this really thought-provoking idea, I think, that the deep secrets held within the fleeting decay of a single bottom quark, they might not only unlock a more complete picture of fundamental reality, but could also genuinely lay the groundwork for revolutionary technological advancements that could really shape our future in unexpected ways.
Amazing stuff.
We are definitely grateful for the insights provided by Yorgo Schneephet's essay, which served as our excellent guide for this exploration today.
Absolutely. Thank you for joining us on this deep dive. Goodbye.
Bye.